So now after the assembly we will go to the steps, uh, create new steps. So there are many steps as you can see. So most basically we use static general and dynamic explicit analysis, implicit analysis, static risks, and any other steps based on your requirement. But the most basically in case of stress strain analysis and this type of analysis is done on static general and explicit, implicit, etc. So we will first create a static general. Nonlinear geometry for if there is high deformation, then keep it on. Incrementation, maximum number of increments, make it at least 10,000. Then increment sign, this is the initial, make it at least 10 or 100 times lower than your time increment. So there is no relation between the calculation time and the actual time. Let's suppose if you are doing a tensile test up to 30 minutes, then it doesn't mean that analysis will run for 30 minutes. So there is no relation between this time period and the actual time. This is your minimum time increment. Dismiss, this is your step. Then go to the field request. This is your output request manager. Domain is whole model and frequency every n increments. So this is how it collect the data from the analysis. You can either create evenly spaced time interval also. So let's make it interval up to evenly spaced time intervals. Let's say 100. This is selected by default. That is stress, strain. You can also select based on your requirement. This is the displacement or translations, forces, reaction forces, concentrated forces, contact energy, and for porous media, void volume fractions, and all that. State and so let's keep it default. This is your history output manager. Keep it default. So energy, that is all types of energy like deformation energy and internal energy. It keeps track of all the energy changes happening in during the deformation. So this is the step. After that interaction, there is I haven't made it according to the let's create a interaction part for interacting. Let's say roller, this is discrete rigid, and base feature is wire. Now go to the, this is your discrete rigid part. Now go to the assembly, roller, and translate this. So this is not going, uh, I'm not going to make any analysis with this. I'm only showing this for the to show you the interaction. So this is your interaction manager, surface to surface contact, self contact, and all that. So this is your surface to surface. There are two options. One is master surface and other one is slave surface. So first select the master surface, then yellow. Choose the slave type. This is your surface. You have selected here a slave surface, then OK. Data are not contact interaction property. So interaction, let's select contact tangential behavior. Friction, you can either choose frictionless or penalty. This is your friction coefficient. And normal behavior, you can make it a hard contact type of behavior. So this here you have created a contact interaction property. So this is the same interaction property manager what we have done earlier, normal behavior and tangential behavior. And this is your constraint manager. So this one here is your rigid body. So let's make it a rigid body. We haven't assigned any reference point to this rigid body. It is very important to assign a reference point. Let's make this a reference point. Now constraint manager, body type, element, select this reference point, this. Now make it OK. So this one here is your rigid body constraint. This section here is your rigid body. So if you are making a contact, as I have said in the impact test or any other where contact surface to surface contact, then you can choose this interaction property manager. Now delete because we don't need it here. I have just made it to show you how we can create interaction between two surfaces. Now move on to the load. So this is here your load module, load manager. There are concentrated force, moment, pressure, and all that. So based on your requirement, you can put concentrated forces and all that. This one here is your boundary condition manager. So let's create boundary condition. If it is in caster or symmetric, anti-symmetric, there are multiple options. If this section doesn't move, then we can make it in caster and all that. Let's make it according to the tensile test. Select this point, and we don't need any movement in the y direction. Then if it is not completely selected, select shift, make it in the x1 direction. So what will happen, the elements on this surface will not move on the x-axis, and elements on this will not move on the y-axis. So if you revolve the total section, it will be a cylindrical. Now create a displacement on this surface. So let's make it 2 mm of displacement. Now dismiss. So this is now there is meshing section. This is your global seeding. If it is saying what it has said, dependent part cannot be edited or assigned mesh attribute. So make it independent. Make independent. Now you can make a meshing. So this is your global seeds, and this is your seeding if you want to seed based on your requirement. So let's seed it here. Approximate size, let's say 0.2 mm. You can also either size it by number of elements, 4, 5, 10, or whatever you want, or based on size. Based on uniformly, it will discriminate. Let's say 0.2. Let's make it 0.8, so it will be more visible. So 0.8, it will make a uniform distance between these nodes. If you want to create either biased in the direction, so what will happen, it has more distance on one side and lesser distance on the other side. You can flip also. And then there is double bias. As you can see, in the central distance is much it is much larger than the other in the other direction. You can also flip it. So based on your requirement, you can choose any of this. Now seed this, let's say 2. This is for create mesh. So this is how it has created a mesh. This is mesh control. It is very important. If you want any specific type of mesh, you need to select it here first. Structure, okay. Delete meshes first. First you need to delete the meshes, quad or either quad dominated. So quad is restricted. It will restrict all the elements to the quad quadratic section. This is free and this is structure quad. So now what will happen? It has created quadratic meshes. These are more regular and they are not free. Now this is here you select the element type. It has already selected the standard and CAX4 R type. You can also choose based on your requirement. I have made it to default axisymmetric type of stresses, 4 node bilinear axisymmetric, and R is for reduced integration scheme. If you remove this reduced integration, it will make it a complete calculation. Otherwise, you can select reduced integration. So based on your requirement, you can choose. You can also choose quadratic. See, then it will be 8 node biquadratic elements. So let's make it CX4R. So here what you have done, you have assigned the element type of to this mesh. This is your to verify the region. If there are any poor elements, it will show you the poor elements. So until you get good meshes, it will not appear. So as you can see, I have made a very poor section here, so it is showing yellow. Now move to the I don't use generally optimization, so directly go to the job. So let's create job tensile. Let's say submission general memory parallelization. Parallelization is mostly used for if you have multiprocessor unit, then use a parallelization. So I have a octa-core system, so I can go up to 16, but if I use 16, then it will throttle and it will not be much faster. If you are doing 8 based on your octa-core, then it will also, you will not be using your full potential of your system. So first you need to make trial and error and see what is the number for your optimum performance. So I have in my laptop I have seen 12 is much better for me. So then, okay, in Abaqus standard, it's not much required, but in if you are doing explicit analysis, it is very important and it can save your lot of time. Now submit it for analysis. Now there is monitor. This is your steps, increment, attributes, equilibrated. So this is your number of increments. This is your total time. So what you have selected 0.001 initially. So this is your initial time increment. It will go up to 1. So here you can see analysis is completed, no errors, and warning it is showing for the poor elements that ATL elements are distorted. That's why it is showing warning. Click on the results. This is your visualization section. Here you can see deform. This is the deformed shape of the object. You can also select the animation. As you can see, this is the deformed section and this is undeformed section and this is deformed. You can select it here. Now I will tell you how to take out the data in the next video. So let's viewport, sweep and extrude sweep element by, this is your axisymmetric analysis. Apply. This is your half section. And you can also make it a mirror to the XZ. So XZ direction. It wasn't connected. So it wasn't connected earlier, that is why there is a space. What you need to do is save. Okay, file name is, let's say, new. Let's see now. Close it and see your folder. This is your this much file it saves when you save it. So this is the file. This file is your main file, that is CAE file. Then there is tensile input files, and one more file is tensile.odb, that is output database. It only opens the output part of your analysis. It only opens the visualization section. You can take out the data, and this is your tensile input file. You can also use some other input files. So this is your input file. This is your element type. These are the nodes of the elements. So based on this data, it creates all the analysis. What you have given here, material name, steel density, elastic plastic. So this much data you can see it from here, and this is your CAE file. You can open it if you want to. Again, let's open the job and results. Okay, so I will tell you how to extract the data in the next video.